So in our residence time distribution development, we talked about the different networks of reactors, and we looked at how to put them together, and we could use that towards estimating the performance of a real reactor. And one of the important topics towards this is that the reactors in series. Just a second here. Yeah, so if we consider reactors in series, right, we can determine an RTD of this whole train of reactors. And by that, we do not mean that we have 3 reactors in series and we are somehow interested in the total RTD of a real train like this. What we are saying is that in our real reactor, it may well be the case that we have 3 well-mixed zones. So for example, if our reactor looks like this, and let's say we have baffles in that reactor, so we have a zone, a well-mixed zone here, and then there's overflow, and we have another well-mixed zone here, and so on. So that's one way that zones could exist. Another possibility simply is that if we have 2 stirrers or more than any number of stirrers in the reactor, then it could be that locally there is a highly mixed zone. So if we have a stirrer here and a stirrer here, even though our intention might be for this to happen, for there to be perfect mixing throughout the whole reactor, it might not turn out that way. It depends on the balance between viscosity and the stirring rate and the other internal. So what might happen is that you get a good circulation rate here and another circulation rate here. You can especially imagine in a low viscosity fluid that you will have locally well-mixed zones, but that energy might not necessarily make it all the way across. So you could easily have different mixed zones in the same reactor. So in a case like that, we can simply model it as if there are multiple CSTRs in series. And so by then connecting with our ideal reactor type, we can simply perform the mass balance, and we can imagine a pulse of tracer as it's passing through each of these stages here. And so doing that thought experiment, as we did many times previously, we start out with a perfect spike on 0, and then we imagine what happens as it passes through each element here. So first, of course, we will get an exponential decay here. And then when it enters the second reactor, there is also going to be an exponential decay of an exponential decay. And so here, we are no longer receiving an instantaneous pulse, right? Over here, we pulsed instantaneously everything in. Here, we are getting tracer appearing immediately, but it's not an instantaneous pulse. So in this case, it takes a little while to build up, and then we get a decay. And that exaggerates further here. And you might say, well, I don't know why we have to take time to build up to that here and so on. So let's see if we can prove this. So we can derive this by taking a material balance. So let's say it's a 3-tank case. And so we are interested in the RTD from that 3rd tank. And if we write our balance, then as we did before, the balance on the 1st tank is that there's some rate of change of tracer. And after T0, so this is written specifically for T greater than the injection time, then we have no further tracer entering, and we only have the tracer that's been held up in the reactor slowly draining out of that. So as before, we have that expression, and we saw that if you do that derivation, okay, it's not here, but here. So if you integrate that, you get that. And then if you divide by the integral under that curve, then you get 1 over tau e to the minus theta over tau. So that's our simple CSTR case. Now, if you do the balance on the second tank, then we can no longer say that after t equals 0, there's no more tracer coming in. Now, because you have tracer held up in the first reactor, that first reactor will always be feeding to the second reactor. So coming out of the first reactor, you will have tracer, and then leaving the second reactor. So this is what comes into the second reactor out of the first reactor, and this is what leaves the second reactor. So the rate of change of the moles of tracer in the second reactor equals the rate at which tracer enters through the exit stream of the first minus that, right? And we have just solved for C1. So we integrated the equation. We've got C1 has that form. And so you substitute that there. And then if you look at this balance, you've got your volume and your flow rates. So if you divide by Q, you can rewrite it in terms of the space-time. So tau I equals VI over Q, right? So the equation looks like this. And then if you look at this equation, you recognize it as an equation. It's an inhomogeneous ordinary differential equation. You can solve it using the integrating factor method. So if you have a look back at your second year maths notes, when you solve it by the integrating factor method, then if you have an equation of this form, the solution is given by this, right? So you take the factor of the term that has the dependent variable in it. So in our case, this factor is simply 1 over tau. So it's not a function of theta, it's just 1 over tau. So that's easy. And then the factor that's an explicit function of your dependent variable, that factor appears here. So that's our alpha. And so if you simply apply this solution, right, this is the solution using the integrating factor method, then you get this expression. And if you apply the limits, then that's your final equation for C2. So you can solve for C2. And you see we have the same e to the minus theta over tau, and we have a 1 over tau, but this time we have a theta there as well. So if you graph this function, you will get a form that looks like this. So it starts from 0, it goes up, and it does that, right? Of course, for a single CSTR, we have a graph that looks like that. So that's a pure exponential decay. So that's 1. And then when you have 2 tanks, then you have this one, right? So that's the solution for 2 tanks in series. And then you can repeat this process. So you can say for the third tank, we have the inlet flow being the exit from the second tank. So that's the contribution there. And then we also lose tracer in the exit stream from the third tank. So you can show that you get an equation of this form. And again, you can do this integration factor method. So you can identify beta and alpha again, and then you get this solution. So now we have a theta squared, and we have a tau squared. So the single tank case was 1 over tau e to the minus theta over tau. Now for the third tank, we have a theta squared extra and an extra 1 over tau. So if you put them all together, you can see a form like this. And of course, we don't want to work in terms of concentrations. We want to work in terms of E's. So you can show, we've said E1 looks like that. And if you do this, if you find the integral in the denominator, then you get that form. So it's simply a tau squared in that case. So E2 looks like this, and E3 looks like that. And you can generally show for any number of tanks in series that that's the formula that you get. And so if you apply this, here's a graph. So this is just using some simple Python code. You can see for the single tank case, you've got this curve like so. Then for the 2 tank case, you've got this orange line here. And then for the 3 tank case, it's the green line there. And so you can see that there is a peak that has started to emerge here. So the 2 tank cases there, the 3 tank case there, the red line is the 4 tank case. And as n goes off to infinity, you are getting what looks like a spike emerging here. So could you have predicted that there is a spike if you let n go to infinity? Any takers on that? Is there a reason why we are starting to see a spike here? So while I'm waiting for hands, I'll just sketch it out here.
Sorry.
Yes.
Is it because the tanks in series start to look like a PFR?
Thank you. That's exactly right. Right. So when you've got your tanks in series, right, with 1 tank, you've got your pure CSTR. But when you are saying that, well, this is actually because I have compartments in my real reactor and I've got multiple little compartments, then it starts to look like we are talking about a plug flow reactor, that each compartment is its own little plug there. So we've got a large number of these compartments. And so we are starting to get what looks like a plug flow reactor. So at 2, we can still see an exponential decay, but as n goes to infinity, the 0 part extends, and then we get the spike appearing, and then it drops like that. And so as n goes to infinity, we get the plug flow. And so what's nice about this tanks in series model is we start from a CSTR, right? N equals 1, there's the CSTR. And then as n goes to infinity, we end up with a plug flow reactor. And so what we have now is a parameter n that can tell us how close it is to the one or the other. So n equals 1 implies a CSTR. N going to infinity implies a PFR. And what that means is we can model the real world case, because in the real world, we are never a pure CSTR, nor are we a pure PFR. In the real world, we are somewhere in between these extrema. And if you think back to your practical, you did measure curves something like this. Didn't your curves look like this when you pulsed tracer in? So most of your curves look like that. And that's because the real world is sitting somewhere in between those two. And it also means that we can then do our real world measurement. So always we can pulse tracer in and measure what comes out. So we can measure that, and we can fit an n value here. So we can say, for example, n equals 4.7. So of course, a fractional reactor is, it's hard to imagine that, but we could imagine a fractional reactor, that's not the same volume as the others. But the point is, we can find a number of tanks, of ideal tanks in series, that's equivalent to our real world mixing. So in the real world, we never mix at, we never achieve perfect mixing, nor do we achieve perfect plugs. So we have now a number that can tell us how much we are like one or the other. So that's your tanks in series model. Then there's another possibility. So we have available the dispersion model. So in the dispersion model, we say, well, let's start from the other perspective. Let's start from a perfect plug flow. So we can say, in our perfect plug, we were only worried about convection, but we know in the real world that in addition to convection as a pure plug, what will actually happen is there'll be diffusion left and right of our plug. So we'll be losing species from that plug. due to diffusion. Now, diffusion is a slightly specific term, and we don't necessarily only mean diffusion, right? For example, this could be a plug of particles, and just because of friction with the walls, those particles are moving left and right of the central plug. So we generalize the concept of diffusion, and we define what we call dispersion. So dispersion means that the plug is dispersing. It's not staying as a pure plug anymore. It's dispersing left and right of that central plug. And so the way we model that is to say, well, before we had the plug part, the plug was convecting along. But now, in addition to that, we need to include a kind of diffusion part or a dispersion part, right? So we introduced this dispersion term. And remember the concept of diffusion. In diffusion, you have your diffusivity and you have a concentration gradient. So it's exactly the same concept. And now what we want is a molar flow. We know diffusivity and concentration gradient, that gives us a molar flux. What we really want is a molar flow rate. So we need to multiply by the area that we are fluxing across, which is the cross-sectional area of that in that reactor. So that's our molar flow rate. And then if we write our balance, we can say the rate of change of moles in our control plug equals the flow in minus the flow out. And then if we recognize that we can rewrite that, well, if we what are we doing here? Okay, so this is just rewriting that. This is just recognizing that these terms, that this difference, we can think of this as a gradient, right? So if we divide through by delta z, then you've got a function at z plus delta z minus a function at z, all divided by delta z. So we can recognize that as a derivative. And so we can say this dc dt equals ddz of f. And so when you do that, then of course we are getting the PDE. So this follows directly from what we learned in fundamentals, right? It's the same kind of balance there. And then if we integrate these equations, you get the so-called dispersion. So you can read up about the boundary conditions. And okay, it's not, the solutions are not drawn here, but let's sketch out the expected solutions. So in the case of the dispersion model, if your dispersion rate is very low, so if that dispersion constant D is equal to 0, then you've got the pure spike as we had before. And then as you relax that and you let D be other values, then you start to get this. So you get dispersion like so. And then as you let D increase higher and higher, it spreads out even further, it starts to do this. And at some stage, you get a curve like this. So what does that curve look like? And so it starts to look like a CSTR, right? In other words, as your dispersion outcompetes your convection, it means that you are mixing laterally. So when your dispersion is some crazy high number, that means we are mixing laterally through here. In other words, we are getting to the state of perfect mixing. So in the dispersion model, equivalently, we start from a PFR and work our way back to the CSTR. And so again, we have a nice model with a parameter that can tell us how close we are to perfect mixing or perfect plug flow. And so the best way to write it is as the Peclet number. So the Peclet number is the ratio of your dispersion and your convection. So that's a nice number that tells us how well mixed we are versus how segregated or how plug-like, right? So that's the dispersion model. So all of those are things that we can use to develop our real-world reactor case. And we talked about this yesterday. We were looking at the compartments in the reactor. So we'll go through examples like this after the test, probably more closer to the second, well, it's test number 3 when we'll cover this RTD material. So we'll probably use some sessions then. I'll also send video links to some of the tutorial materials where all this is covered in further detail. Okay, any questions or comments on any of this? Okay, so I'm just going to